Waiting for mortgage rates to drop could be a costly mistake. Once rates drop, new home buyers will enter the market and prices will soar even higher. At Churchill Mortgage, you can get a free analysis and learn how to avoid the trap of waiting for interest rates to drop. Buy now and refi later at churchillmortgage.com. This is a paid advertisement. NMLS ID 1591. NMLS ConsumerAccess.org. Equal Housing Lender. 1749 Mallory Lane, Suite 100, Brentwood, Tennessee 37027.
Experiences are what people love the most about travel. That's why they love Viator. They have over 300,000 bookable experiences and something for everyone. Plus, their travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. Download the Viator app now and use code Viator10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
Hello, thanks for joining us. This is Space Nuts. I'm Andrew Dunkley, your host, and it's so good to have your company once again. And coming up on this episode, it is all questions because it's episode 350, and that's when we dedicate our show to the audience to nail down such questions as those of stellar mass black holes, our place in the universe and where that place might be in the future because it's moving. Is there a size limit to rocky planets? We're going to look at expansion limits, expansion effects, asteroids, space-time, and photons. All questions coming from our vast audience of 9 here on Space Nuts. Hope you can hang around a while.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to discuss all of that and much, much more is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Very good to be at large again.
Yeah. They haven't caught you yet. They haven't caught you yet.
Found me.
Not at all. We've got a smashing program. There's so much to talk about today. So I think we'll just hoe straight in and get stuck into it. And our very first question comes from none other than...
Hello, Space Nuts. Martin Berman Gorvine here, writer extraordinaire in many genres. And today we're crossing my strengths in science fiction with horror as we ask, how close could a spacecraft with human beings aboard realistically get to a stellar mass black hole before all the people inside are fried and or linguinified, which I think sounds better than spaghettified, don't you? Can't wait to hear the answer. Martin Berman Gorvine in Potomac, Maryland here, over and out.
Linguinified. Yeah, we
I
can
like
work
it.
with that. Yeah,
Yes.
we can work with that.
Yeah.
That's not bad. How close is too close? So I suppose the answer is it depends.
It does, doesn't it? Yeah. So somewhere in here we go. This is the usual tribute to one of my books, but I can't remember which one or which chapter.
That's 5 episodes in a row.
You know. It's all right. I'm not naming any. At least I don't think I'm going to. I did write about the event horizon diameter of a stellar mass black hole, and I can't remember what it is, but it's relatively compact, measured in kilometers, if I remember rightly. But the event horizon's not really what would sort you out in the answer to Martin's question. Because yes, you'd be linguinified, spaghettified. You probably would even be risotto-fied as well, because you might end up in bits.
Right.
When you got within a much closer distance. Here's something I'm pulling out of my memory from only about 4 weeks ago. There's a gas cloud which is currently orbiting it's not orbiting, it's passing by the supermassive black hole at the centre of our galaxy. Now, that's not a stellar mass black hole, which is what Martin's asking about. This is a 3.6 million stellar mass black hole. This gas cloud is passing within a few trillion kilometres, if I remember rightly, of the black hole, and it is being spaghettified. And it's been watched, it's been observed to do that over quite a long period. Notwithstanding that, a few more trillion kilometres, there are stars happily in orbit around the supermassive black hole. So I haven't done the calculation, Martin. It's probably conjecture as to, at what level do the tidal forces separating your head and your feet start to become significant enough that they overcome the atomic forces which are holding your atoms together.
Wow.
And that's a calculation that I haven't done. But even for a stellar mass black hole, it's probably not very far away. I think the tidal forces that you would experience would really start to make things uncomfortable.
Okay. And which one is the stellar mass black hole again, in terms of the size of black holes?
It's the mass of one star.
Stellar mass is one star, right? Okay,
yeah.
Gotcha.
Hence the name. Yeah, sorry, I'm being glib there, but that's right. It's an object of the order of the mass of one star, which sometimes includes things up to 20 or 30 times the mass of the sun.
Yeah,
but it's still not a supermassive black hole, and it's not the other thing that we've talked about from time to time, the intermediate mass black holes, things of order 1,000 times the mass of the sun. Which are quite rare, we believe.
And very much unlike the ultramassive black hole that we talked about a few weeks ago.
Yeah, that's right.
Yes,
Bigger
bigger than big.
Bigger than big, yes. Just wait for the hypermassive black hole. That's the next one to come.
Well, it could happen, couldn't it?
Indeed, it could.
You just never know. These things, like when we started the podcast and right through several episodes, or several years of episodes, we could only confirm there were two.
Indeed,
types,
yes,
small and large. And now we've got
loads,
loads of different,
and including that ultramassive black hole that we talked about. That's sort of pushing the limits of which we thought black holes could exist. We thought they couldn't exist. I can't remember what it was. Was it 30 billion or thereabouts? Can't remember the figure.
It was some
like that,
astronomical number.
It was a huge number.
Yeah, it was amazing. So the answer to Martin's question is, in real terms, you could get reasonably close, but
not that close.
But not that close.
Sorry, Martin, we haven't given you an answer at all, have we? We just talked about it.
But reasonably close is what?
I think
millions of kilometres.
Yeah, I don't think you'd want to get. If it was at the centre of the solar system, I don't think you'd want to get much nearer than Saturn or Neptune.
Oh, right.
Sorry, or Uranus. So, yeah.
Well, no one wants to get near that.
No, indeed.
Now, okay. So, Martin, that's a very loose answer to your question. But it's a good question because, one day we might be able to get out there and get close to one of these things. And you really need to do your mathematics before you lined yourself up.
Bring it home.
Came out of your space warp. Oops, I mentioned the name. And got too close.
Yeah.
All right. Thanks, Martin. Great to hear from you. Let's go to a text question. This actually came in via email from Andrew. He says, hi, love the show. I have a science question. Does our sun move its position as the planets orbit? If so, by how much? Thanks, Andrew. Hit reply to respond. No, we'll just talk about it.
Yeah, it's a great question. And the answer is yes, it does. And so the bottom line here is that the sun, in a sense, is not the centre of the solar system. The point at the centre of the solar system is something called the barycenter, which is the sort of, it's like the centre of gravity of the solar system. So it includes not just the sun, but also the planets, of which really only one counts in this argument, and that's the planet Jupiter, which is the most massive of the solar system's planets. but the barycenter, that's to say this center of gravity, does actually move around with respect to the sun, or should I say the sun moves around with respect to the barycenter. And it's that process that actually allows us to detect the planets of other stars, because if you've got a object in deep space, a star, 100 light years away, all you can observe is its light and its spectrum, but what you can see is its velocity changing slightly as the planets pull it, slightly one way or the other, and you can actually disentangle how many planets there are around a star without being able to see any of them, just by knowing how the star moves with respect to the barycenter. It's that movement that you can see reflected in the star's velocity. And in fact, we can now detect motions of stars with an accuracy measured, believe it or not, in centimeters per second, rather than, the work I did, you were doing well if you got down to a kilometer per second accuracy. But meter per second accuracy has been attainable for a long time, but now people are talking about centimeter per second accuracy in the speed of a star that you can detect. If I remember rightly, the planet Jupiter changes the sun's velocity by around 11 meters per second.
Is that right?
To detect, to detect a Jupiter-sized planet in the same orbit as Jupiter is, but around another star rather than the sun, you would see motions of that star of 11 meters per second as it moves with respect to the barycenter. Now, Andrew's other part of his question was, how much does it move? How much does the sun move with respect to the center of gravity of the solar system? And it's basically not much, but that barycenter does actually, from time to time, it is outside the sun rather than being within it. So you're talking about the sun moving by, some fraction of its diameter, and it might be quite a large fraction. It's not millions of kilometers. It's, actually, the sun is 1.4 million kilometers in diameter. So it might be millions of kilometers, but more likely to be tens or hundreds of thousands. That's which means that the barycenter is, for the most part, inside the sun, but it does occasionally go outside. When you include the effect of all the planets, that includes Saturn as well as Jupiter.
I suppose the other way to describe the movement would be that wobble we talk about when they're trying to detect planets around other stars. That's one of the methods, isn't it? The wobble?
Yeah, exactly. That wobble is the 11 kilometers per second in the case of Jupiter around the sun. The Doppler wobble technique, it's called.
Yeah. Yep. Very good. Thanks, Andrew. Hope you're doing well. Let's go on to our next question. This comes from Tom in Ireland. He said, "Hi, my brain hurts. Please help." Paracetamol or ibuprofen is very good for that, Tom. 13.8 billion years ago, the universe began and has been expanding ever since. How is it that we can see objects up to 12 billion light years away in one direction and also in the opposite direction? If we are seeing these objects where they were 12 billion years ago, which means they were 24 billion years apart, how could they have originated at the same point 13.8 billion years ago? Please help. Love the show. Tom in Ireland. I think he's getting his light years and his universal age years mixed up, possibly.
No, it's a confusing thing. Because and your age years is a good point, because we talk in terms of look back times. That's the kind of usual phrase, and so it's misleading to say a galaxy is 12 billion light years away, unless you qualify it by adding in the co-moving coordinate system, and not many people do.
I know I don't.
No, there you go. So. The bottom, it's better to talk in terms of look-back times, because that's the sort of fundamental thing. When you see an object in the very distant universe, you're seeing it as it was maybe when the universe was 1.8 billion years old, if it's got a 12 billion year look-back time. But its actual distance is much more than 12 billion light years, because the universe has expanded by a huge amount since the light left that object. So the what you might call, in fact, it's got a name. It's called the proper distance. Would be something like 30, maybe 35 billion light years away because of the expansion of the universe. But that's something that you can't actually measure in any way, that distance, because all we see is the light that's reached us after its 12 billion year journey. And so it's more accurate to talk about look-back time of 4 billion years than to say a distance of a look-back time of 12 billion years rather than a distance of 12 billion light years, unless you say it's a co-moving distance, which is the distance which doesn't account for the expansion of the universe.
Good grief. It kind of equates to the question we often get about where is the center of the universe and where we are. Where are we in it? Well, we are in it.
That's right.
Technically speaking.
Yeah. So, sorry, and Tom, I didn't really answer probably or address your question about things being separated by 24 billion light years. And that's all that is saying, yes, we see things receding from us in different directions, and the Hubble law seems to work everywhere, whatever direction you look in, and the Hubble law is the one that relates. It's this velocity, the velocity away from us of an object to its distance. It's how we know that redshift equals distance in a standard cosmological model of the universe. So what that is telling you is that the universe, first of all, is extremely big. And we think that when it kicked off within the first gazillionth of a second, in fact, about 10 to the minus 33 of a second, if I remember the number rightly, it expanded very violently in this period we call the age of inflation, which only lasted a few quintillionths of a second, but blew up the universe from the size of a pea to the size of a galaxy. And then the expansion sort of settled down. But that's how we think. That's why we think the universe looks the same in all directions, even though it's very, very large and the distances separating objects is very, very extreme. We think at one time everything was very close together, and then it wasn't. And that's why we see what we see today.
Okay. Tom's headache is throbbing now.
Yes, probably, yeah. I go for aspirins, actually.
You do? Oh, okay.
Yeah.
I just go around trying to find willow trees and lick the bark.
Okay. All right. I wondered what you were doing.
That's a natural painkiller.
I didn't know that.
Yeah. I think that's how aspirin was invented, wasn't it?
There you go.
Not sure. Something like that. Willow has a natural pain-killing property in it. It does. Thank you, Tom. Great to hear from you. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
When you download the Baker's app, you have easy access to savings every day. Get the most out of weekly sales and receive personalized coupons to save on your favorite items, all while earning 1 fuel point for every $1 spent. Baker's makes it easy to save while you shop, whether it's in-store or online, so you get the most value out of every trip, every time. Download the Baker's app now to save big on your next purchase. Baker's, fresh for everyone. Must have a digital account to redeem offers. Restrictions may apply. See site for details.
The holidays start here at Baker's with a variety of options to celebrate traditions old and new. Whether you're making a traditional roasted turkey or spicy turkey tacos, your go-to shrimp cocktail, or your first Cajun risotto, Baker's has all the freshest ingredients to embrace your traditions. Baker's, fresh for everyone.
Choose from a great selection of digital coupons and use them up to 5 times in one transaction. Check our app for details. Baker's, fresh for everyone.
Space Nuts.
Now, Fred, to a regular contributor to our question and answer session, and it's Duncan from Weymouth, I think. I'm pretty sure he'll tell me that's where he's from.
Hello, Duncan here from Weymouth in the UK. Another quick question. I know that Andrew likes hypothetical ones, so here's one that's been bugging me for a while. If you could get a huge mass of rock together, say I don't know, 100 times Jupiter's mass of solid rock in one place and put it in, I don't know, orbit around a star, would it form a really massive rocky planet? Or is there an upper limit as to how big or how massive a rocky planet can be? Just interested to know. And if it couldn't form a massive, massive rocky planet, what would actually happen to that rock to prevent it becoming a rocky planet? Would it somehow not be able to be bound together, or would it melt or boil and form a gas, or what would prevent that? Okay, keep up the good work, and thanks for your efforts. Bye.
Bye. Thank you, Duncan. I reckon it'd become a Kuiper belt or an asteroid belt or something like that if it couldn't form a planet. Would have to sort of break up like that. But how big's the limit? I suppose that's the question.
That's right. So, yeah, it's a really interesting question. And I think the limit is imposed not by the physics of how big something can be. It's more about how things evolve when planetary systems are formed. So we think that rocky planets do evolve by the sort of silica material in the original dust and gas cloud that formed the solar system. We think that stuff all stuck together, became solidified, turned into rock. These bits of rock bashed into one another. Some stuck together, some didn't. But in the end, you got planets building into rocks building into planetesimals, and then to protoplanets, and eventually to planets. But this is all taking place within an environment that is very, very gassy. And if you form rocky cores that start getting very big, you will also amass gas. You won't just accrete rock; you'll accrete gas as well. And that's why we think the gas giants are gas giants, because they grew big enough that they not only collected more bits of rock, they actually collected very significant envelopes of gas around them. And it's sort of helped as well by the what we call the frost line or the ice line in the solar system. That region, which is between the orbits of Mars and Jupiter, where ice actually forms because the temperature is low enough. Yeah, and so the limits are more about the way you form planets rather than what could exist. Whether 100 Jupiter mass solid, 100 Jupiter mass object is actually a star, because I think the mass limits for brown dwarfs is it 13 Jupiter masses up to about 80, I think. In something in that range will produce deuterium burning and become what's called a brown dwarf star. But if you get above that, then you've got a dwarf star. But that's assuming it's made of gas. I think that the physics prevents you from forming a rocky planet with anything like that kind of mass, because it would accrete gas rather than accrete just more rock.
Okay, yeah.
That's the best I can do, Duncan.
That's pretty good, though. I think we are discovering rocky planets that are much, much bigger than Earth.
Yeah, they're sort of up to Neptune mass. But and they're called super Earths. So what that's saying is that we perhaps haven't achieved that limit within the solar system.
Yeah. Well, in the scheme of things, our rocky little world is actually one of the smaller ones, isn't it, in real terms?
Yeah, although it's hard to, the bottom line is that we're not really yet able to detect all the smaller planets that are around stars, because it's harder to detect them. You can do, and there are programs that let you do that. Gravitational lensing's one. Transit method lets you do it as well. But perhaps the Kepler and TESS spacecraft have both contributed many objects which are small compared with, what we used to be finding, which were always the Jupiter mass things and bigger. So we are finding rocky planets, but there's still, I think, gaps in our knowledge because we haven't got the technology yet to find the smallest ones.
So when we get that perfected, we might find a whole bunch of Earth-sized rocky planets.
And things that are smaller than Earth as well.
Yeah. Okay. Thanks, Duncan. Always good to hear from you. Jim is next. He's from something I can't pronounce. New Orleans? Yeah, New Orleans. It's Jim. Dear Professor Watson and Mr. Dunkley, I've been travelling by car a lot in the past year and was able to catch up on all your podcasts thus far. Blimey. I truly enjoy the show and look forward to the next episode. Onto my question. Because the bodies in the universe are accelerating at an ever-increasing rate, eventually there will come a time when space-time will become impracticable, or space travel will become impracticable, if not impossible. What I mean is that eventually, as a result of increasing acceleration, the velocity at which galaxies and their component parts move through the universe will attain a substantial percentage of the speed of light. If we cannot build spacecraft that attain speeds greater than that substantial percentage of the speed of light, then it seems that when a spaceship leaves the Earth's gravity well, the Earth will become unreachable by the spaceship because the spaceship cannot catch up. Can this be right? There must be something that I'm missing. Thanks for your thoughts. Have a great day, Jim. That's I can see where he's coming from. It is a quandary. And yes, we have talked about the fact that as things expand, we're eventually just going to be totally isolated in the universe and we won't be able to see anything else, which is due to happen in a couple of days. But
Put it in your diary.
Yeah, indeed. So what's the answer to Jim's quandary?
Well, I think Jim's on the money actually, because yes, if we look into the distant future when the expansion has accelerated, so that you're talking about a hugely greater expansion of space-time than we have at the moment, things will disappear beyond the horizon because the light that's leaving them now will never catch up with the expansion of the universe, so we won't see them. And that's the point that you were just making, Andrew, that we will have a very lonely existence when you look a few trillion years perhaps down the track, because there won't be anything other than the local group of galaxies visible. Maybe the local group will disappear as well. And I suppose what Jim's question about the spacecraft really means is that if the spacecraft could get far enough from the Earth so that it was being carried away from the Earth due to the expansion of the universe at a velocity higher than the velocity the spaceship could achieve, then yes, you're right, you wouldn't be able to get back. You'd never make it back. It's an interesting conjecture, and a universe very different from the one we live in today, thankfully.
Yeah, it's a horrifying thought, though, isn't it? Let's go visit that rock. Oops.
Yeah. It's gone.
Yeah, and we can't get back. Not good. Thank you, Jim. On a similar kind of playing field, Paul in Melbourne says, there has been talk recently about the energy that causes the universe to expand coming from black holes. If this is so, then wouldn't we see the space-time around or near a black hole expanding at a faster rate than that further away from black holes, for example, between galaxies, or that in the spaces between the filaments of the cosmic web? Wouldn't the filaments of the cosmic web be expanding faster? And there's Fred's answer.
Yeah, I'm just trying to remember what the mechanism was that linked, and I can't quite get my head to it, that linked black holes with the dark energy, which is what is the thing that we think drives the expansion of the universe. Dark energy seems to be very much a property of space itself, a uniform property that's the same wherever you look. So Paul's question is an interesting one. I can't remember the exact link between the mechanisms within black holes and the dark energy, because yes, it's an intuitive thought. If dark energy is coming from black holes, then the region around black holes should be expanding more than the region elsewhere. But we already observe the fact that that doesn't happen. We do see space-time distorted around black holes, but that's due to their gravitational attraction. That's the standard general relativity distortion of space-time that we see, whenever we find gravitational lenses, for example. So, as I said, the point about dark energy is it is a phenomenon that is a property of space. I would have to, I'd have to look back at what I was reading up on the mechanism that feeds the energy of black holes into the space around them to be able to give an answer to Paul's question. So I'm a bit embarrassed that I can't do that. I mean, it was about, it must have been at least 2 months ago when we talked about this.
Yeah, I guess so.
It's a
I do
great
remember
story,
the
though.
conversation, but I just can't recall the...
It is that paper, I don't think has been refuted, the one that suggests that maybe black holes could provide the origin of dark energy. And I wish I could... there's a point about it which I'm just not able to recover at the moment from the memory banks.
Yeah, and I could have a quick look and see if I can find the article, but gosh, I don't know. There's plenty of articles about it, so which one do you pick? But it certainly got a lot of interest at the time.
It did, and that will continue. And
we're talking mid-February when that first came out. So it's fair enough that at our age we've forgotten.
At least we remember the article was there.
Yes. Yes, indeed.
So, Paul, I might try and look at that again, and we might get back to you if we don't forget this entire conversation.
I'll put an asterisk next to his question. Follow up. All right. Thank you, Paul. Thanks for sending in the question. This is Space Nuts Andrew Dunkley here with Professor Fred Watson.
When you download the Baker's app, you have easy access to savings every day. Get the most out of weekly sales and receive personalized coupons to save on your favorite items, all while earning 1 fuel point for every $1 spent. Baker's makes it easy to save while you shop, whether it's in-store or online, so you get the most value out of every trip, every time. Download the Baker's app now to save big on your next purchase. Baker's, fresh for everyone. Must have a digital account to redeem offers. Restrictions may apply. See site for details.
3, 2, 1.
Space Nuts.
Okay, Fred, a few more questions before we wrap it up. And this one comes from Western Australia, our good friend Rusty, actually, to be more specific, Rusty's wife.
Hello, Space Nuts. It's Rusty in Donnybrook. My lovely wife Ollie came up with a question about asteroids. And she's seen a few movies with asteroid fields in them and wonders if they're realistic, how close do they get, and how often do they collide? And I'm sure she'd love your answer. Cheers.
Thanks, Rusty. Asteroids, they're not an uncommon topic of questions either, mainly the ones that are going to hit us or near hit us. But a different spin on it, so to speak.
And a good one too. Great question, because when you look at depictions of the solar system, the main asteroid belt, which sits between the orbits of Mars and Jupiter, is always portrayed as being full of asteroids. Asteroids everywhere, in every direction. Whereas the bottom line here is, Douglas Adams' famous quotation, "Space is big. You won't believe how big it is." Anyway, it's big. What was it? You might think it's a long way down the street.
You might think it's a long way down the street to the chemist.
Chemist, that's right. Anyway, there is a lot of space between them. So, as witnessed by the fact that I can't remember how many it is. It must be this 5, 6, 7, about 8 or 9 spacecraft have gone through the asteroid belt, including Galileo, Cassini, 2 Voyagers, 2 Pioneers, New Horizons. They've all gone through the asteroid belt and, of course, been completely unscathed. On having said that, the second part of Rusty's wife's question, I'm sorry I didn't catch your name, but the second part is, do they collide? And the answer is yes. From time to time they do, which we see usually as a plume of material coming from an asteroid that's being accidentally observed, usually because it's part of the field of view of something else. So some nondescript asteroid will suddenly start looking like a comet. It'll get a tail of material, a bit like Dimorphos did after it was clouted by the DART spacecraft. So you get this usually reasonably straight-line cloud of material, which is interpreted as having been a collision between two asteroids. We think we've even observed one in the planetary system of another star. The star is Fomalhaut. It's a bright star in our southern skies, and over a number of years, that's been observed to have an object going around it. We covered this, I think, a year or so ago, Andrew, which was thought to be a planet that gradually got fainter and eventually disappeared.
That's right.
And the thinking is that what we actually were looking at was the debris cloud from two large asteroids that had collided, because that thing's vanished altogether now as the debris cloud disperses. So they do collide. Relatively rarely, because the space between them is so big.
Yeah, I mean, going back a few billion years, it was probably a lot more collisions. There's a lot more stuff out there to hit each other in closer proximity.
In fact, that we give that period a name. It's called the Late Heavy Bombardment, about 3.8 billion years ago, when the place was full of debris charging around and bashing into other things.
Including Earth.
including Earth. That's right, indeed.
Thanks, Rusty and Spouse. Let's go on to our next question from Rennie.
Hi, this is Rennie from West Hills, California, with another question. I'm trying to understand what space-time is made of and why it bends when it interacts with matter. I envision space-time as an invisible energy force pushing against an object of matter, which is another form of energy, where the two find a balance, which is gravity. Am I correct?
Yes. And the answer to your question is it's made up of space and time.
Yeah, that's the trouble. Nobody really knows what space-time is.
No.
But I can qualify that a little bit further, because whatever it is, we glibly talk about the fabric of space-time bending under the action of mass. René's quite right. It's really hard to get your head around that, because back in the 1880s, we got rid of the idea that there was an ether, something that actually permeated space and allowed light to pass through, a medium that would transmit light. That got thrown out, and the consequence of that was actually the special theory of relativity, which says that the speed of light is the same everywhere, because the experiments, the Michelson-Morley experiment, as it was called, to measure the ether, relied on the fact that you should see the speed of light changing depending on what direction you're moving through the ether. And we're not moving through the ether, so the speed of light doesn't change, and that then brings up special theory of relativity. So we really don't know what it is, but I think you have to look at the big picture here, because the big picture says, well, there are two sort of pivotal theories on which we base our view of reality. General relativity, which works incredibly well for things on a large scale, and quantum mechanics, which works incredibly well for things on a small scale. But the two are incompatible. They don't sort of sit together. And that sparked, back in Einstein's day, actually, the quest for a theory of quantum gravity that would allow us to unite these two theories, which we're still looking for. But one of the themes that I think is addressed by quantum gravitists, if I can put them that way, theoretical physicists who work on this, one of the themes is that we're missing something.
Yeah.
And what we're missing is a more fundamental theory of space and time that underpins what we see as space and time. In other words, there might be something else that from which space and time emerge, and hence space-time. Many quantum theorists in the last 20 years have proposed that. And most of the theories, I mean, string theory is one of those. It's that sort of idea that there's something there that underpins what we observe in relativity and in quantum mechanics, and a kind of deeper version of reality, which may include additional dimensions. There is some recent work that's being done on this, which we might talk about in coming weeks, Andrew, that once again highlights that there might be this hidden reality beneath space and time, which, how do we probe it? That's the problem. And the suggestions that are being put forward for how we might deal with that in a real situation, how we might actually try and peer underneath the gossamer veil. Well, no, it's not a gossamer veil, it's an opaque curtain of relativity, and on the other side, quantum mechanics.
Also known as the banking industry.
Oh, the banking industry's got that as well, a different reality.
They have.
In fact, yes, I think there are many places in the world where you can point to different realities.
Yeah, indeed. Thank you, Rennie, and hope that helped somewhat. Now, adequately. Now, finally, we'll go to David, who is from Huntsville, Alabama. First of all, I'm a huge fan of the show and appreciate what you guys do to put new wrinkles in my brain. I look forward to each Thursday for my Space Nuts fix. My question is, if a photon does not experience time after it's been emitted and the universe is expanding greater than the speed of light, assuming the photon has an unimpeded line straight towards the edge of the universe, is the photon essentially trapped in time at that point? Thanks. Keep up the great work. Kind of relates to a question we had earlier.
It does, yeah. And it presupposes the universe has an edge, which we don't think it has. We don't know what it's got, but we don't think it has an edge.
It's got a banking industry surrounding it, isn't it? A opaque veil.
So if the photon, to the photon, it's always traveling through the universe at the speed of light. Now, the fact that it's the source of the photon and its destination are being separated by the expansion of the universe at greater than the speed of light, doesn't matter to the photon. It just keeps on going. The fact that its target is moving away from it faster than it's ever going to get there is not a concern to the photon. It will still not experience the passage of time, which is exactly what David said. That's what we think is the case. And we'll just keep going forever. I suppose, in a sense, it's the scenario that he mentioned, that it will just keep on passing through space ad infinitum, because its destination is not good, is always going to be further away than it will reach.
Until the big rip.
Until the big rip, yeah, that's right.
An escape.
Yeah.
Maybe. Well, if there's a big rip, there'll be tidal forces beyond imagination that would probably disturb everything as it.
Yes, that's right. I think the
apart.
big rip has got consequences that we can't really envisage at the moment, but it's definitely not nice.
And it reminds me of that famous song, "I'm a photon and I'm okay. I glow all day and I glow all night and I glow all day." Stealing from Monty Python.
Monty Python, yeah.
Yeah, not quite, but it's close.
It nearly works as well as the original Lumberjack song. Yes, that's right.
Yes.
The photon
Thank
song,
you, David. It's so great to hear from you, and thanks to everyone who's sending questions. It's nice to fill an episode with audience questions, and we got a whole fresh batch like 1 minute before we started, so that was good, and that's why some of them sort of caught us out of left field, because
I'm afraid it did. Yeah,
we did what we usually do and went in totally unprepared. Sometimes works. So if you do have a question for us, of course, send it to us, because that's what it's all about. We love to interact with you, and we love to hear your voices. So you can record through our website, spacenutspodcast.com or spacenuts.io. Click on the AMA link and you can record a question there, or send us a text question, or you can just hit the tab on the right-hand side of the home page send us your voice message. And as long as you've got a smart device or a computer or something dumber than that that's got a microphone, you can send us a question. But we're taking text and audio questions all the time. The more the merrier. And yes, don't forget the hypotheticals. I love those hypotheticals. Fred, we're wrapping it up for yet another. It's a milestone.
It is
episode,
a milestone,
actually.
isn't it?
350.
I mean,
we kind of let that slip through the keeper.
I can't believe it. 350.
Yeah, 350. Oh my gosh, it seems like only 6 months ago we did probably a year ago we did episode 300. Gosh, that
would be right, wouldn't it? Yes, that would be right.
It'd have to be near a year.
It would, yes. There's a calculation there.
I'm not going to do it.
The words "we should get a life" really come to mind.
Yes, maybe we should. Thank you, Fred, as always.
Good to talk, Andrew. Take care.
All right, we'll catch you soon. Fred Watson, astronomer at large, part of the team here at Space Nuts, and back at Space Nuts HQ, we say thanks to Hugh for reasons we cannot comprehend. But anyway, thank you anyway. And from me, Andrew Dunkley, thanks for joining us each and every week, and for this latest episode. We'll catch you on the very next one on Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.